Guess how old that is? That jar of fluid. This is a jar of nickels in water that I've had for over 18 years. These nickels ended up in this water as a result of a course. I was a non-conventional college student. I went back to school in my 30s. Back in 1998, 99, somewhere in there, I had a transition metal chemistry course. And we were assigned a metal to identify and to produce products with. And we identified our metal as nickel. So at home, I gathered up some nickels, which is not hard to do, and put them in a solution of water. Actually, I put them in a solution of hydrochloric acid, muriatic acid, knowing that the oxidation potential of nickel is low enough to where you can actually, with a little bit of heat applied, you can actually get that nickel to come off into solution. And then you can produce products with it, nickel carbonate, nickel hydroxide, things like that. The reason that I'm showing this to you is this has to do with the Permian extinction, and this has to do with the global warming issue with runaway methane and the fear that excessive amounts of CO2 in the environment will cause the ocean to become acidic, and that there's some discussion I've seen online about that. The theory is that global warming because of CO2 is what caused the Permian extinction. It's very important to point out that the Permian extinction, I've already done a video on this, during the Permian extinction, there was also the introduction of about 4 trillion tons of hydrogen sulfide, which is important because what I'm showing you here, if you put nickels in water, then what you end up with is this green substance here, which I believe is nickel carbonate. Nickels have copper and zinc and other things in them. There's a plug that nickels are actually made out of, and that the plating on it is actually made of nickel, but the plug has got copper in it. When I first did this experiment, I was ending up with copper in my solution, and so there was a question that I went back to my instructor with: how is it that because of the oxidation potential of copper is not really low enough for me to have copper in solution because of muriatic acid? In other words, muriatic acid is not strong enough to consume the copper. And his name was Dr. Bieber, interestingly enough. Don't know if he's related to the Beeb, but his name was Dr. Bieber at Santa Fe Community College in lovely Gainesville, Florida. And Dr. Bieber suggested that it might be sulfides from the air, or maybe even nitrates or something like that. My contention was that's impossible because the sample was always indoors. So how was it that I was able to identify that I was getting copper out of the solution? Because whenever I would take my stainless steel pocket knife, I had a pocket knife made by Spiderco back then, which was Japanese stainless steel. The copper would plate out on the stainless pretty effectively. And if you would throw a piece of aluminum into the solution, the aluminum would jet around like a little motorboat around the surface of the solution as the aluminum was being rapidly oxidized. Kind of sort of discovered what I postulated was that what was really happening was I was ending up with hydroxyl radical, an OH radical, nickel OH plus, that has the oxidation potential, plenty of oxidation potential to oxidize that copper and put it in solution. And that's kind of sort of that's what I reasoned it out to be. But in any case, the upshot of all that is that if you leave a glass of water out eventually, if I leave it out overnight, then by tomorrow morning, it's going to taste a little bit different. It's going to taste different because it has absorbed the gases in the air and, whatever funky things have been floating in the air, pollen and what have you. But one thing that's going to have in spades is carbon dioxide. Carbon dioxide is just enormously soluble in water. It readily dissolves into water. So if you leave a cup of water out overnight, you end up with water that has a significant amount of carbon dioxide in it. Well, in this case, if you leave like these nickels here, if you leave them in a glass of water like this for a period of time, a week or something like that, in a week's time, you will notice that you have nickels that have this corrosion on them. Probably nickel oxide. I think the green apple color is the nickel carbonate, if I remember correctly. But most of the carbonates, hydroxides, and what else do we have? Oxides, I believe, of nickel are they're greenish in color, and a few of the copper oxides are like that as well. So, but that's what you end up with after about a week. And that's, of course, because the carbon dioxide dissolves in the water and oxidizes the metal and puts it into solution. And then eventually there is a change in the pH that the metal will actually turn that carbon dioxide. The carbon dioxide turns into carbonate. The chemical reaction produces nickel carbonate, which is not soluble. And it precipitates out of the solution. And that's what you see here, this material on the bottom of this glass here is actually probably nickel carbonate and maybe some other copper compounds that are floating around there, and they're not soluble. So that just precipitates out of the solution. Well, this is the same thing that happens in the ocean. The ocean, because of smokers, volcanic smokers on the bottom of the ocean and so forth, is got tons and tons and tons of metals, insoluble oxides or insoluble carbonates of various metals will just precipitate out onto the ocean floor. So the carbon gets eaten up over time. The carbon gets turned into carbonate and precipitates out onto the ocean floor. That is, unless you introduce hydrogen sulfide in large quantities, which makes the ocean acidic. And when you make the ocean acidic, that acid doesn't allow the metal carbonates to form. If I saw correctly, I believe the ocean has got a pH, well, it probably varies, but the pH is around 8.2 to 8.4, somewhere in there. So when you lower the pH, the carbon dioxide is less likely to be consumed by the metal ions that are floating around in the ocean, less likely to be turned into some sort of metal carbonate and precipitated harmlessly out onto the seafloor. So there it is. So sans hydrogen sulfide, I can't see that we would have, just from methane alone, just from carbon dioxide alone, I don't see how it is that we could possibly have another Permian type extinction. It's just my personal belief, and I could be wrong. It's just my personal belief that it's the hydrogen sulfide in combination with the carbon dioxide, the methane and carbon dioxide, that caused the Permian extinction. Without that massive amounts of hydrogen sulfide to lower the pH, make the oceans more acidic, the carbon dioxide would have been consumed more rapidly. But I have seen other work.
Right. So remember, when we raise the temperature, the ocean starts losing its gases, which is the one most important gas in the ocean is oxygen. And all the animals use that oxygen, right? So we start losing oxygen. What happens in the ocean? Acidification leads to sudden acidification of the oceans, right? And what that leads to, animals going to start dying because they are now starved of the oxygen, right? So there's no oxygen, and the ocean is more acidic, right? So it's getting more and more acidic. What other factor happens with that? There are bacteria which live without oxygen, right? In the environments where there's less oxygen, they thrive. They thrive, and what do? They decompose the inorganic matter, which is dying now. What it leads to? Formation of another gas called H2S. And H2S is poisonous, so it's gonna kill all the animals within the ocean. And when it comes out, it starts affecting the land animals as well. So this is what happened. The land animals also went extinct, 70% of them, because the ocean had a major impact on them as well. When the acidification happened and all these bacteria were producing all this gas here, this led to now affect animals as well. Other factor was, when I said insects, so insect went extinct, 83%. And what it leads to, all the flowering plants depend on insects, right? So those are going to go extinct as well, or they're going to die as well. And that is exactly what happened in that time.
Well, I thought this was going to be a simpler vlog tonight. I was just going to do a little bit about the nickels and go on, and I was looking at something that I already knew, but I just kind of wanted to look it up. Carbonates are frequently insoluble. Group 2 carbonates, calcium, strontium, barium are insoluble. Some other insoluble carbonates include iron carbonate and lead carbonate, interestingly enough. So that's just a given. This is something that I knew. I didn't really have to look it up. You don't really, there's no scale or anything because most carbonates are insoluble. That's just how it is. But just kind of looking around for a little additional support on my general thesis here of how carbonates are basically scavenged by metal ions and turned into insoluble carbonates and precipitated out on the ocean floor. I ran across this little interesting tidbit here: corrosive seawater, not low pH, implicated as cause of. I had to go and see what the hell this was. Corrosive seawater, not low pH, implicated as cause of oyster deaths. So then it's really rather confusing. Now we look down here. This is Figure 1 images of the ancient fossil calcifier Discoaster, before left and during right. The Paleocene, Eocene thermal maximum, PETM, about 56 million years ago. Both creatures lived at times when the atmospheric concentration of CO2 was much higher than present day and ocean pH was lower. But the fossil in the right-hand image lived when carbonate ion abundance and carbonate saturation was also low. This was due to a rapid increase in atmospheric CO2, which caused seawater to become corrosive to calcium carbonate forms. It's just like, okay, is anybody else totally confused by this? Both creatures lived at a time when atmospheric concentration of CO2 was much higher than present day and ocean pH was lower. But the fossil in the right-hand image lived when carbonate ion abundance and carbonate saturation was also low. This was due to a rapid increase in atmospheric CO2, which caused and I'm just totally kind of sort of, what the fuck are these people talking about? Is it just me? Leave a comment. I mean, that's just, this is like totally, this seems totally, this is like a contradictory kind of something or another. I'm not really sure what exactly it is that they're saying here. But it's an interesting article nevertheless. They're saying, it says right up here at the top, corrosive seawater, not low pH, implicated as cause of oyster deaths. So, and you see how this relationship between carbonate and, oh, here we go. Oolite sand. Hydrogenous sediment formed when calcium carbonate precipitates from warm seawater as pH rises. forms rounded grains around a shell, fragment, or other particle resembling fish eggs. So, you get the feeling that there are things that are made to be way more freaking complicated than they need to be, that are somehow or another less straightforward than they should be, or presented in a way that is less straightforward than it should be. So this is something that's constantly annoyed me. Textbooks where the material is presented in just this in a circular kind of way. It's as though it's intended to just confuse the shit out of you. So I don't know. This seems somehow or another strange, circular and counterintuitive, and kind of like a strange kind of way. So if anybody gets this, the link is in the description. Leave a comment. My name is R. Crosby Lyles, and this is News from the Can. Thanks for watching. Don't forget to drop us a like if you like the material, and comment and subscribe. Thanks for watching. See you. News from the Can.